Going live. I'm live. Excellent. We will be finishing it today. Yes, we'll be finishing it today. Let me do my little rundown. Actually, let me do my little speech first. So, originally, okay, well, actually, no, let me back up a little bit. I got to tell the story from a much earlier time period. Teachers every year have to be observed by their superiors. They have to be observed, and then that superior grades that teacher on a certain scale, blah, 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 blah. Teachers get a score every year. We get a score on this model that's out of 4. And as long as we maintain a score of approximately 2.68 or higher, then we're fine. If we score under 2.68 or lower, then you are put in a probationary stance. And then if you don't improve upon that the next year, then they have cause to get rid of you. See, like people be like, oh, teachers got tenure. It's like, okay, there's no such thing as tenure. There's no such tenure. Basically, well, okay. When you get hired, you go through like this 3-year kind of like not interim, but like kind of like probationary period where you're untenured in order to gain tenure, which they're trying to determine, okay, are you working here, blah, 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 the whole thing. And then once you get past your period, then it becomes much more difficult to get rid of you. So if you're within that first 3 years, they can just get rid of you. They don't even have to have a reason. Yeah, but if you get past that first 3-year period, you walk in like day 1 of your 4th year, then now it's not really tenure, but now they have to have cause to get rid of you. So I was supposed to be getting observed today. Yes, now it's not happening. Nah, I don't care. Honestly, I don't care whether or not I get observed. I don't even really mind that they're here. I mean, if they want to come in and watch, it's perfectly fine. Yeah, they should. Yeah, I wouldn't put that on the live stream though. I get kicked off of YouTube. No, but I was so excited. Because so I was supposed to get observed by Panulo today in this class, and yeah, so he and I sat down last Thursday or Friday, and he's just like, so I can come by like second period on Tuesday. I'm like, that's great. He was like, what are you teaching? I'm like, I'm teaching cryptology. He's like, what's the lesson? I explained to him the lesson and how it fits into everything else that we've been doing, because I was going to teach you something new today. And I still am, by the way. And I was getting really excited. We started talking about this and the other thing, talking about the imitation game, the Enigma machines, all this other stuff. And he was just like, okay. And I'm like, yeah, heck yeah. And then I ran into him yesterday, and he's like, yeah, I can't make it by. Like, okay. So, I know. I know, we should, just because. No. So check this out. Teachers are graded on a model of 4 domains. Domains 1 through 4, according to this thing called the Danielson model. No, the first 3 domains are about you as a teacher. You know, your knowledge set, your ability to talk to students, whatever, your ability to teach, your organizational skills, and all this other stuff. But then the 4th domain is like basically, okay, domains 1 through 3 are what we actually pay you to do. What are you doing extra? Like, wait, what? Like, so like the people who do well in domain 4 are the people who like they go to like sporting events and they volunteer, do this and they do that, and blah blah blah. And it's like, that's not fair to some teachers. Like, yeah, lives and kids and like things to do and live like an hour away. I mean, I live like 5 minutes away, but still. Anyway. My wife made this bow tie. Yeah, you should be jealous.
I'd be jealous if I didn't disdain the whole Star Wars May calendar.
Okay. Way to be a wet blanket.
Yeah, wet blanket. Bro,
wet blanket.
Not wet. It's not.
All right, whatever. Anyway, for those of you in the live chat, hopefully you can see my little bow tie right there. I'm trying to let it focus on the camera. My wife made it. Anyway. Back to this. You're a people. So as for today, number 1, you did have an assessment due for me. I believe it was the modular minor. There it is. I can see the people who've turned that in. If you haven't gotten that done, please make sure that you do. Ooh.
Oh yeah, I mean.
What happened to the internet?
Oh, someone hit a power pole.
Yeah, that whole area. No internet.
Oh, was it on Lighthouse? Oh. Oh, nice. Oh, Gunning River Road. All right. Well, get that to me as soon as you can, because you say just this morning. Whatever. Anyway, it's supposed to be a straightforward minor. But anyway, as for today, I am going to be introducing a slightly new topic. I say slightly new because it is going to be based on a lot of the stuff that we have been doing. Do a little bit of an intro song and dance routine. It'd be great. And then we'll get into that. And then, well, after that, because there's a kind of a lengthy introduction to it and teaching you what it is and stuff. And then we will finish the imitation game today. In terms of what I'm going to be introducing to you today, it's what I was supposed to be observed on. So Panulo is like, oh, can I come by on Thursday? I'm like, yeah, sure. He's like, is it going to be a different lesson? I'm like, yeah, it's going to be a different lesson. He's not going to watch a movie, but it's going to be basically, I'm going to expand upon what I taught on Tuesday, and we're going to be getting into some more trickier situations. It's going to be nice. We'll see how it goes. Anyway, so if you do not already have them out, I need those notebooks out and open. I see you there, Sky. If Sky, email me, maybe not from the minor itself, but email me a couple of like specific questions about it or broad questions about it, and I can get back to you, because I would like to hear what you have to say on that, so that I can kind of guide. I don't know. So we have been doing modular arithmetic in order to encode messages. It's been wonderful. Let me take you on a journey. In the beginning of the semester, I introduced you to this concept of monoalphabetic ciphers. Just the general idea that we can rearrange an alphabet and create a cipher alphabet in order to encode our messages. But these cipher alphabets in the beginning of the semester were based on a keyword. So, for example, I would write A through Z, and then we would have some kind of keyword, like the word, I don't know, cloud or some junk like that. And so I would be like, okay, well, here is A, B, C, D, E, F, G, H, etc. That would be my plain text, and then this would be my cipher, C, L, O, U, D, and then we would continue the cipher alphabet from that letter D, where we would go E, F, G, and then etc., and then we can't repeat letters. We did that in the beginning of the year. We talked about the concepts of polyalphabetic ciphers and things of that nature, but I just wanted to focus on this one real quick. The monoalphabetic cipher, well, it's based on a keyword. You don't have to memorize the whole alphabet. You just got to memorize that keyword. But it became very apparent, wouldn't it be better if we just had a completely randomized alphabet? What, say it again?
It's already randomized because you put it in that order.
Well, they could if they knew the keyword. What if it was completely randomized? There's a huge problem with a completely randomized cipher alphabet. How are you going to memorize it? How are you, or the person that you're sending the message to, going to memorize it? Well, what if there's no keyword? I'm just saying, like, now this isn't completely randomized. This is using a keyword, and then the rest of the alphabet follows as such. But what if the whole thing was completely randomized? That would be difficult to memorize. Sure. No, we can't do that. So I actually introduced to you the idea of a randomized alphabet. I did. We haven't really talked about it being a randomized alphabet. Let me flip my screen over. Right here. There is the randomized alphabet. You can use this mod 26 table to have a completely randomized alphabet. Because now, like, for example, pick a number up here that's not even and not the number 13. 7. He said 7. So I'm going to look at row 7. And for row 7, I'm going to have this randomized alphabet where it's like, it says 0, 7, 14, right? So it's like, hold on. Here is the plain text alphabet up top, right? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, etc. And then it goes, okay, well, here is the cipher alphabet. A, H, O, and then it would go from there. I'll finish it. L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. So then 18 would be, no, I'm sorry, 21 would be V, and then 2 would be C, and then 9 would be J, and then 16 would be Q, and then 23 would be X. Now, isn't that like what you would determine, to, not completely randomized, but like, is that a randomized alphabet? Yeah, it's kind of nice. And you don't have to memorize it, because as long as you have this table or know how to do mod 26 with these numbers, then you got it. It's all golden. But here's the problem. Let's say that somebody knows that you did a completely randomized alphabet. How many of these rows are we allowed to use? Yeah, less than half. We can't use any of the even ones because they repeat. They are divisible by 2, and 26 is divisible by 2. So we can't use any of the even ones. Why can't we use 13? Only 0 and 13. Do you know why there's only 0s and 13s? Yeah. We could use prime numbers, yeah. But the thing is that I want to point out is what Josh just said before. Josh, you said less than half. There are 26 rows here, and we can only use like 12 of them. So if somebody knows that you did like a completely randomized alphabet, they're like, well, there's only one of 12 to choose from. Just keep going up. Yeah. Say again? Well, here's the thing. If we do a mod bigger than 26, that would assume you have more letters than 26 letters. You know what I'm saying? Well, I mean, you could do a larger mod. In fact, you could do something like a mod 52. You could do a mod 52 in which like you and the receiver know that the first half are capital and the lowercase or second half are lowercase. But again, it just repeats. So that actually wouldn't be that great. But if you and the receiver had a condition of like these extra things were like symbols, then you'd have an argument on your hand. But there's really only 12 to choose from. So let me bring a link up on the screen real quick. I always forget what this website is, but you guys remember this, right? It's the Caesar wheel. What if, you see how all the letters go from A to Z in order on the blue and the green? What if they didn't? What if instead of A to Z on the green, it was that completely randomized alphabet that we just came up with? And not only was it that completely randomized alphabet, but we were also able to shift it over like a Caesar wheel. We would have many more choices. Instead of 12 choices, we would have 12 times 25 choices. Yeah, you can't do 26. So you do 26, you'd end up back where you started, you know? So it's like 12 times 25, 300 choices. Instead of 12 randomized alphabets, you'd have 300 randomized alphabets. This is the idea of what I want to introduce to you today. Today, I am going to show you not only a cipher alphabet that uses multiplication, but a cipher alphabet that uses addition at the same time. It's the 2-in-1 special. It combines the idea of multiplication and addition at the same time in order to expand your 12 randomized alphabets up to 300 potential alphabets. Yeah. Now, if somebody were doing this by brute force, Or, like you said, guessing. They could easily guess one of the 12. If it was just a Caesar shift, there's only 25 to choose from. They could easily guess that too. But if it was a combination of both, they could still eventually guess 300. But it will take much, much longer. So, today is May 4th. You know, I have to tell you, I just recently rewatched The Force Awakens. It's better than I remember it to be. But The Last Jedi is still terrible. No one agrees. All right. Then you all are dead to me.
Oh, it's The Last Jedi? Yeah, it's still terrible. I forget the names because I didn't watch it.
I gotcha.
We watched last week, Miss Lozzie. We watched the new book.
Oh, really?
Yeah.
It's the archetypal story. It's like the hero's journey.
Yeah.
You know, is that why you guys did it? Nice. Yeah. Yeah, because it does borrow a lot from a lot of like famous Japanese movies from like the 50s and stuff.
I was like,
Yeah.
that'd be the fifth time watching it.
I gotcha. Okay. The Affine cipher. Oh yeah, Sky says yes, we did for class. Nice. The Affine cipher. It is a combination of the addition and multiplication ciphers. Multiplication ciphers. There we go. She said her favorite part about Star Wars is that I'm confused. Wait, what? My favorite part about Star Wars is that I'm confused, but it's still a good series? I guess. I don't know. You know, it's a really good movie? Rogue One.
Yeah.
Just saying. That's a good one.
He uses the ending of everyone dies, the end.
No, but I mean, it works within the canon of the movie.
They stuck it in really well, but I didn't
Yeah.
like that everyone dies.
Whatever. Actually, one of the guys from that movie is getting his own spin-off show.
Which one?
You'll see. Anyway, back to this. No, not that guy. Although that guy was awesome. Yeah. All right. Combination of addition and multiplication ciphers. Now, typically, the way that it works out is like this. Oh, wow. Sky's getting her own spin-off series.
Pretty wet.
Nice. Now, I know you said like K-pop, but no. K times P plus N mod 26, where P is your plain text number. So not only are you going to be multiplying that plain text number by something, but then you are also going to be shifting it over, Caesar wheel style, by adding an additional number, mod 26. Now the key is this. The GCD of K and 26 has to be equal to 1. The greatest common divisor of those two numbers has to be equal to 1. That goes to our multiplication wheel. Your value of K cannot be even, and it cannot be 13. Otherwise, you cannot use it. The value of N can be any of those numbers that we just talked about. In fact, the value of N, let's just say, can be anywhere between 1 and 25. The value of N can be anywhere between 1 and 25. Technically, I guess you could say the value of K could be between 0 and 25. But that's neither here nor there. We're going to pick numbers somewhere in between. It's going to be nice. So now I'm going to have you guys. Well, do I really want you to do that one? Yeah, let's do one. You pick two numbers between 0 and 25. But remember, for the k value, it has to be odd and it can't be 13.
11.
For which one?
The K value.
For k? Okay, we'll pick 11, and now we need one for the n. 7. 11 and 7. So we'll let k equal 11 and n equal 7. Good to go. That's what we're going to do here. Here's my function. F of x equals 11x plus 7. Now that x is acting as the plain text. That x is acting as the p, so to speak. But I'm putting it in terms of this equation so that it's a bit more familiar to the algebra aspect of it all. Let's figure out the word hello. And let's actually try to encipher the word hello. We all know the word hello, hopefully. What letter of the alphabet is H in this case? Hold on, we can figure this out. So A is 0, B, C, D, E, F, G, H is 7, right? Okay, just making sure. 7. Again, A is 0, B, C, D, E. E is 4. B, C, D, E, F, G, H, I, J, K. L. L is 11. That makes sense because N, remember what number N always is, right? 13, which means that O is if N is 13, what's O? You said N was what? So what's O? 14.
That's what I was saying. Then you're like,
I didn't hear you. Did anyone hear him say 14?
I heard him say 14.
You did?
Yes.
You are defending Josh right now.
Yes, I am.
Anyway, back to this.
I said it, and he was like, "Are you sure about that?"
So if I were to take each of these numbers, the 7, the 4, the 11s, and the 14, and put them into this function, f of 7, if you did this calculation correctly, would be, well, 7 times 11 plus 7, that would give you 84. But of course, we can't leave it as 84. How are we going to reduce the 26? So we got to reduce this thing mod 26. Now, if you actually do that, where you're like, okay, 84 minus 26, there you go. It goes down to 6, which what letter is 6 on this alphabet?
Wait.
No, it's a little. I know. It is the weirdest thing. Let me do it like this then. Let me put this along the bottom here. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, and Z. And then this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. There we go. Just for the sake of argument, I'll leave that there. So then the number 6 corresponds to what? Yeah. It's corresponding to a G. So then f of 4, if you were to plug that thing in and do the multiplication, you would get 51. But of course, you would have to mod 26 it. So if you do 51 mod 26, it actually becomes a 25. And that 25 is what, Z? There we go. Now the L repeats, so I don't have to do this calculation twice. But if I do f of 11, I get 128. If you do mod 26, you get 24. that 24, what is that, Y, and that happens twice. And that F of 14 becomes 161, which is the equivalent of 5. What is 5? F?
Yeah.
Sweet. So as a result, hello, when you encipher it, becomes G, Z, Y, Y, F. That is the enciphering. Now, I will tell you, flat out, that the enciphering for this is very straightforward. There is no craziness that is involved, nothing out of the ordinary in terms of encoding this stuff, enciphering. You simply just pick the appropriate numbers like you guys did according to the rules. Your K value cannot have a common factor of 26. Can't be divided by 2, can't be divided by 13. N can be anything you want. It's got to be between, 0 and 25. Or 1 and 25, I believe. Yeah, I don't think it can be 0. But then it's like, oh, just plug the appropriate number in, reduce it mod 26, and there we go. We can get the cipher alphabet. Wonderful. Yay, if only all of life were this easy. Let's try to decode it. Can you hear the ominous tones in my voice?
Saying this, Mark, right? You get two people with calculators. If you know that it's an affine cipher,
Yep.
two people with calculators could probably bang out 26 of these in 2 hours.
26 of these?
Yes. Two people not working on the same one. They would start from the ends of the alphabets. They go down.
Well, let me ask you this, though. You ready?
No.
If you encode it, moving forward, you go from plain text to ciphertext. My opinion is when you go from plain text to ciphertext, it's very straightforward, very kind of, I don't want to say easy, right? But for the lack of a better term, it's like boom, 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 got it. Is that fair? Yeah. Now cipher to plain text. Decoding. It's not as straightforward as you think. One might argue, and in fact, I am going to have you write this down because I want to get to this real quick. I'm sorry, Sky. Let's try to decode this thing. So let's say you are given the ciphertext of G, Z, Y, Y, F. And you are told that this is an affine cipher or affine cipher, whatever you want to call it, with the following numbers. Now, actually, they would give it to you just like that, by the way. They would say, like, they'd give you like an ordered pair, and you would assume the first one is the multiplication and the second one is the addition. Very straightforward. And so you're sent this secret message from your friend across the hall. And you're like, man, I wonder what they said. Now, one might argue, oh, okay, you could do frequency analysis. Okay, you totally could do frequency analysis, except we only have 5 letters. That's true. You could totally bully them. Yeah. I mean, this word could be anything. It could be the word hello. It could also be the word bully. You never know, because you got that double Y in there, right? But you're told that it's an affine cipher. Meaning, okay, the function that is being used is 11x plus 7. And you are told to get this answer. So, okay, let's work through this a piece at a time. G, Z, Y, Y, F, we know correspond to the numbers 6, 25, 24, 24, 5. We know that. We can see the alphabet at the bottom of the screen. So now we have to work ourselves backwards. So now, hold on. I want to put a little note here. I want to put a little asterisk here, and I want you to put this asterisk into your notes. What we're about to do will not work. What we're about to do on this page with this asterisk will not work. But I still want you to write it down. There's a reason. I need you to see why it doesn't work. So we could work backwards with this affine cipher. I think I'm going to call it affine for the fun of it.
Is that how it's really pronounced?
Actually, Liston and I were talking about that. He doesn't know. I'm like, is it affine or is it affine? He's like, Anyway. So let's work on that G. If I'm going to work backwards, this calculation right here produced the G. Remember before we did that calculation where we plugged in the number and it, after everything was all said and done, it produced that 6 at the end? Let's solve this. How would I solve this? How would I solve this? Tell me, how do I get X by itself, algebra geniuses?
I'm almost failing algebra.
This is like pre-algebra.
All right, guys, let's subtract the 7.
Yeah, let's subtract that 7.
You gotta divide.
Wait a minute. If I divide, I'm going to get a decimal. Huh.
Looks like.
Hold on. If we divide, we get a decimal. I love what Sky just said in the chat. She said, not a decimal with a broken heart. If we divide, we get a decimal, which is impossible. It's impossible.
No, you can just get half the letter.
Nope.
What are you, silly?
Nope. It's impossible. You can't do it. So the thing is, I'm sorry, let me rephrase. You can't do it this way. You can't do it this way. Here's the thing. The reason why it didn't work, the reason why this calculation gets a decimal is because we did not account for the modular. After we did that calculation with 11 times x plus 7, we've reduced that number mod 26. It's not that, okay, we've reduced it mod 26. How far was it reduced? I don't know. No stinking clue. So we have to figure out an alternate way of getting this thing done. Question. Why would you divide by 11? But why divide? So you said I have to divide because 11 was being multiplied. So what's the deal there? What's the deal with multiplication and division? What's the deal with multiplication and division? They are inverse operations. Now, we are going to have to perform the inverse on 11 in regards to mod 26. Now, the way that I'm going to write that is like this. Move this up. Put a little asterisk here. This will work. We are going to have to divide by 11, but not in the way that you really think we're going to divide by.
How else you would divide?
You see what I wrote there?
I hate that. Stop it.
That
How you divide?
represents the inverse operation of times, I should put times, of quote, times 11. That is the inverse operation of times 11. Question.
Not yet.
Not yet?
No.
Question. What happens when two inverse operations come into contact with each other?
Cancel out.
They cancel out.
This.
Now answer me this even farther. Ready? What happens when a multiplication and a division inverse come into contact with each other? They cancel out, but what do they cancel out to become? Say again? 1. Now that's the key here. This operation here, now this may seem strange at first, but you're going to love where this is going once I get there. You're going to love where I'm going with this. We have to figure out what times 11 mod 26 results in a 1. That's what we have to figure out.
What's your guess, Josh? What's your guess?
You don't have to guess.
That was a trick question.
You ready? You ready?
Yeah.
Now let me repeat the question. Let me repeat the question. And let me write down the question so you can do this. We need to find quote, what times 11 will result in a 1, end quote. We need to find what times 11 will result in a 1. And if we find that number, then instead of 11 to the negative first power, we can replace that with the number that we need. Let's see. Hold on. I'm going to freeze the screen, and I'm going to change my my camera over. Hold on. See if I can find it. Right here. Let's see. Get this thing ready for you. I'm going to blow your minds wide open. Because in reality, we already know the answer. It may seem like a ridiculous question. It may seem like this question is like, what the heck is he even talking about? Back to here real quick. Let me repeat it. What times 11 will result in a 1? You ready? This is the moment. What times 11 will result in a 1? And he's correct.
Boom. How? Did you look or did you just guess? I still think your Josh Powers is correct.
What times 11 will result in a 1?
Close, you said close.
I said 19.
19. This is a multiplication chart. This is a multiplication chart, ladies and gentlemen. When you go 19 times 11, somebody, you have a calculator, do 19 times 11. And tell me what that resulting number is.
Wait, 209.
209? 209. Now, 209 mod 26. 209 mod 26. Now, if you do 209 mod 26, you can do it one of two ways. In fact, just hit like minus 26 and keep hitting enter until you get to the smallest possible positive number. It's a 1. This is a multiplication chart mod 26. This multiplication chart is going to basically give you the multiplicative inverse that you need. So you weren't guessing. He got it. That's just 1 for the day. No, but I'm being serious. You don't have to go, like, here's the thing. There is a long way to get there. There's a very long way to get to that answer of 19, which at first, that's what I was doing. I did like 2 pages worth of work, and I'm like, there's no way I'm going to teach it this way. So I went to Liston, and I'm like, Liston, is there a shorter way to do this? And he's like, why, yes. Use that chart.
We've gotten that without using the original answer.
Yep.
But now, if 2 people figured out how to do that, now you just start adding things.
That's true.
Subtracting things.
That's very true. But keep in mind that any code, not any code, but most codes in history can be cracked.
My original estimate of 2 hours is a bit off.
Yeah.
Probably by around 24, but give or take.
So the 11 inverse is 19 because of the mod 26 chart. So instead of 11 inverse times -1, we're going to go 19 times -1 equals x. Which you could do 19 times -1. What is it? -19. Now, we can't deal with negative numbers here. So you have a calculator, don't you? What's -19 plus 26? 7. Hey, what letter of the alphabet corresponds to 7? H. Remember what we're trying to decode?
And this is like the long way.
No, this is the short way. Eventually, I'm going to show you how you can program this crap into Excel, but that's not today.
I wish you did that at the start of the year, so we just be done with all of this right at the start of the year. It's a computer coding class.
I know, that would have been actually very interesting. I hadn't thought about that until literally Liston's like, oh yeah, you can have them do it in Excel. And I'm like, really? And he's just like, yeah, you just introduce stuff and you show them how to use the formulas. I'm like, can I do that at the beginning of the semester? He's like, oh, I've never done it that way. So now, check this out. Move this stuff up. It's going to become a lot nicer to do this, because check this out now. F of x equals 11x plus 7. Was that our original formula?
Yes.
Yeah. F of x minus 7 equals 11x, correct? Now, don't we have to divide by 11 here? I don't want to divide by 11. But if we're doing mod 26, what is the inverse of 11 that we're going to use? What is the multiplicative inverse of 11 that we are going to use? What am I going to replace that with? Right there.
19.
You're going to replace it with a 19. It should be 19 times this. Now, keep in mind one thing. This is day 1. Day 1 of seeing this stuff. I am not expecting you to be a master and genius of this method right off the bat. I'm not. This is day 1. But this is the calculation that would have to take place. So now let me bring back these letters off to the side. G, Z, Y, Y, F, which correspond to 6, 25, 24, 24, and 5. If you were to take those numbers and plug them in like we talked about, 6 minus 7, this equals negative 19, which is the equivalent of 7. 7 becomes an H. We could do, what's the next number, 25? 19 times 25 minus 7. Let's do this one here. First of all, 25 minus 7. You have a calculator. What's 25 minus 7? 18. 18 times 19. 18 times 19. You have a calculator. 342. 342 mod 26. Hold on, 342 mod 26. You can do it a number of different ways. You get 4, which is mod 26. But what letter corresponds to the number 4? E. And you can see the word hello beginning to emerge. This is the way we'd have to do it. Technically, it is kind of working backwards, but the method does require the use of modular arithmetic. It does require the use of figuring out that 19, which you can get thanks to that mod 26 chart. It's kind of nice. It is kind of nice. Now, let's actually finish this thing out, and then I'll wrap up today so we can get to the rest of the movie. 19 times this calculation. I'll just do this one real quick. I finally got a calculator up and running. 323. Oh, by the way, 323. Let me show you this real quick. Zooming in, zooming in, zooming in, zooming in, zooming in, zooming in. Check this out. Do you remember the other way I showed you how to do mod? Divide by 26. Get rid of the whole number. Multiply it by 26. You get 11. So 323 is equivalent of 11, but what letter is 11 according to that chart? L. It's a double L. And then finally, the last number we're plugging in is a 5. 5 minus 7. We're going to get a negative number here. This is negative 2 times 19 is negative 38. It's easier with the negative 38 if you just add 26. So like negative 38 plus 26 plus 26, you get 14. And 14 corresponds to what now? O. And there's the number hello, or there's the word hello, deciphered. This was a lot nicer to figure out because they gave you the numbers 11 and 7. They gave you the numbers 11 and 7. Basically, what you're going to have to do with 11 and 7, notice what it did here. I subtracted the 7, and, well, we had to multiply by the inverse of 11, which the inverse 11 ended up being 19. That's basically going to be the procedure. Well, how do we get the inverse of 11? Well, you go to that chart. You go to the proper row, and as Josh did, you look for the 1. And once you get that 1, you nailed it. It's going to be nice. It will be. Encoding is straightforward. Decoding is going to be slightly icky. You know it's going to be even ickier? Do you know what's even ickier?
Just destroy it, just randomize it somehow.
What if they didn't give you the 11 and the 7? If they didn't give you the 11 and the 7, and you had a long message to decode, there is a way to do it, which involves systems of linear equations. I'm so excited. That's not today, though. Sorry, you guys are missing all the comments that Sky is making. Okay, but yeah. So on Thursday, we are going to get some practice with the beginning steps. We are going to get practice with encoding and decoding various messages using Affine ciphers. And we'll see how far we can take this. It'll be quite nice. In the meantime, for those of you in the live chat, we're about to transition to watch the rest of the movie. So I do see the 3 of you that have left comments in the live chat. Thank you for those. But we are going to transition to the end of the movie. We left off at an hour 30. And we are going to take the next half an hour and finish the rest of the movie, basically. So I am going to sign off on the live stream because I can't show the movie on the live stream. But for those of you in that live stream, the link to get there is the same as last time. Oh, yeah, hurry up, because we got a movie to watch. I'm going to post that link in the live chat here. So there's that link that we used, the P2B TV. You can sign in, get to 1 hour and 30 minutes, 1 hour, 30 minutes, and finish the movie. And that's exactly what we're going to do. And then I will see you guys on Thursday. So for those of you in the live chat, I'm going to sign off, and then I'm going to get this movie set up. Yay!